Hello, welcome to our coating and deposition laboratories at ICAU. I'm Farnia Rashman, the graduate Master of Solid-State Physics student with distinction honor as top student in my class. Today, I would eagerly like to describe and demonstrate some equipments and techniques in our laboratories, which we use to promote our solid-state physics knowledge as experimental one. Here, all the projects are supervised by Professor Dr. Hanlari. We try to apply cutting-edge techniques for obtaining significant results in this field, especially growth and deposition of thin films and also fabrication of semiconductor nanostructures due to their vast applications, and also investigation of these systems' properties by different methods of spectroscopy. In material science, the sol-gel process is a method for producing solid materials from small molecules. The method is used for the fabrication of metal oxides, especially the oxides of silicon and titanium. The process involves conversion of monomers into colloidal solution, sol, that acts as the precursor for an integrated network or gel of either discrete particles or network polymers. Typical precursors are a metal alkoxide. One of the equipments in our laboratory is atomic force microscopy. Atomic force microscopy or scanning force microscopy is a very high resolution type of scanning probe microscopy with demonstrated resolution on the order of fractions of nanometer, more than 1000 times better than the optical diffraction limit. Using an atomic force microscope, it's possible to measure a roughness of a sample surface at a high resolution to distinguish a sample based on its mechanical properties. For example, hardness and roughness, and in addition to perform a microfabrication of a sample, for example an atomic manipulation. In the field of semiconductor physics, for example an identification of atoms at the surface, evaluation of an interaction between a specific atom and its neighboring atoms, and a change in physical properties arising from a change in an atomic arrangement through the atomic manipulation have been studied. In the field of cellular biology, for example, an attempt to distinguish cancer cells and normal cells based on a hardness of cells and an attempt to evaluate of an interaction between a specific cell and its neighboring cells in a competitive culture systems have been made. In some variations, electric potential can also be scanned using conducting cantilevers. In more advanced version, currents can be passed through the tips to probe the electrical conductivity or transport of the underlying surface, but this is much more challenging, with a few research groups reporting consistent data. The information is gathered by feeling or touching the surface with a mechanical probe. Piezoelectric elements that facilitate tiny but accurate and precise movements on electronic command enable the very precise scanning. The operation methods of AFM are generally classified into image formation and the others. The image formation is a plotting methods as a color mapping, similar kind, or color mapping is introduced as a function of the origin through the changing the x, y position of the tip by scanning and corresponding some particular amount a measured variable, the intensity of control signal to each xy coordinates. In this respect, the color mapping is a method which corresponds a value, a measured value, and etc. to each coordinate and shows it. It means the image which specially expresses the intensity of a value as a hue. Usually, the correspondence between the intensity of a value and a hue is shown as a color scale in the explanatory notes. The other groups include various matters such as force spectroscopy and potential mapping. This is spray pyrolysis deposition equipment, and it's the main method which I have used to obtained significant results in my master project. During the last several decades, coating technologies have garnered considerable attention, mainly due to their functional advantage over bulk materials, processing flexibility, and cost considerations. Thin films coating may be deposited using physical methods or chemical methods. The chemical methods can be split according to a gas phase deposition or a liquid phase deposition, where chemical vapor deposition and atomic layer epitaxy are the gas process. Here, I would like to explain about one of the part of my master project, which I got significant results and published it in International Journal of Latest Research in Science and Technology as paper. As its abstract, I should refer to the transparent semiconductor and aluminum doped zinc oxide thin films were prepared on silicon substrates by sphere pyrolysis method, followed by in air annealing, zinc acetate dehydrate 2-methoxyethanol and aluminum nitrate were used as a starting material, a solvent, and a dopant source respectively. X-ray diffraction pattern shows that the annealing process improves the crystallinity of the aluminum doped zinc oxide thin films. The mechanism of blue-green luminescence of aluminum doped zinc oxide thin films are analyzed. Energy dispersive X-rays or the EDX were used to analyze the composition of aluminum doped zinc oxide films. And the morphology of the AZO thin films is studied by atomic force microscopy and field emission scanning electron microscopy analysis. Average diameter of some also obtained nanorods is approximately 60 nanometers. One of the other growth method which I have experienced in my master project is chemical vapor deposition for fabricating ZNS thin films and ZNS nanowire on silicon substrates. As it's demonstrated, the devices is in running for fabricating these nanostructure systems. Chemical vapor deposition is a chemical process used to produce high quality, high performance solid materials. The process is often used in the semiconductor industry to produce thin films. In typical CVD, the wafer substrate is exposed to one or more volatile precursors which react and or decompose on the substrate surface to produce the desired deposit. Frequently, volatile byproducts are also produced, which are removed by gas flow through the reaction chamber. Microfabrication processes widely use chemical vapor deposition to deposit material in various forms, including monocrystalline, polycrystalline, amorphous, and epitaxial. These materials include silicon such as SiO2, germanium, carbide, nitride, and oxynitride, carbon such as fiber, nanofibers, nanotubes, diamonds, and graphene, fluorocarbons, filament, tungsten, titanium nitride, and various high-K dielectrics. This is the equipment of ultraviolet visible spectroscopy in our laboratory. Ultraviolet visible spectroscopy or ultraviolet visible spectrophotometry refers to absorption spectroscopy or reflectance spectroscopy in the ultraviolet visible spectral region. This means it uses light in the visible and adjacent near UV and near infrared and IR range. The absorption or reflectance in the visible range directly affects the perceived color of the chemicals involved. In this region of the electromagnetic spectrum, molecules undergo electronic transitions. This technique is complementary to fluorescence spectroscopy in that fluorescence deals with transitions from the excited state to the ground state, while absorption measures transitions from the ground state to the excited state. Molecules containing p-bound electrons or non-bonding electrons and electrons can absorb the energy in the form of ultraviolet or visible light to excite these electrons to higher antibonding molecular orbitals. The more easily excited the electrons, for example, lower energy gap between the HOMO and the LUMO, the longer the wavelength of light it can absorb. This is the physical vapor deposition equipment in our laboratory. Physical vapor deposition, or PVD, describes a variety of vacuum deposition methods which can be used to produce thin films. PVD uses physical processes such as heating or sputtering to produce a vapor of material which is then deposited on the object, which requires coating. PVD is used in the manufacture of items which requires thin films for mechanical, optical, chemical, or electronic functions. Examples include semiconductor devices such as thin film solar panels. This is one of the furnaces in our laboratory which we use for annealing process. Annealing in metallography and material science is a heat treatment that alters the physical and sometimes chemical properties of a material to increase its ductility and reduce its hardness, making it more workable. It involves heating a material to above its recrystallization temperature, maintaining a suitable temperature, and then cooling. In annealing, atoms migrate in the crystal lattice and the number of dislocations decreases, leading to the change in ductility and hardness. In the cases of copper, steel, silver, and brass, this process is performed by heating the material, generally under glowing for a while, and then slowly letting it cool to room temperature in still air. Copper, silver, and brass can be cooled slowly in air or quickly by quenching in water, unlike ferrous metals such as steel, which must be cooled slowly to anneal. In this fashion, the metal is softened and prepared for further work such as shaping, stamping, or forming. Annealing occurs by the diffusion of atoms within a solid material so that the material progresses towards its equilibrium state. Heat increases the rate of diffusion by providing the energy needed to break bonds. The movement of atoms has the effect of redistributing and eradicating the dislocation in metals and to a lesser extent in ceramics. These alterations to exciting dislocation allows the metal objects to deform more easily, increasing its ductility.